Hi guys, so I wanted to review the hybridization one last time just because I felt like it was really important to understand and really simple, but just needed to be presented in another way. And so I have examples of compounds. They're actually from the inside back cover of your workbook. The example compounds for each of the geometries. I'm going to go through them just so that we can understand the hybridization a lot better. So with the first one we have beryllium chloride, so 2. And so with this one, beryllium, when we look at the periodic table, we see that that one is a 1s2, 2s2. And so with the configuration, we only have to worry about the valence electrons because those are the only electrons we do chemistry with. We don't do chemistry with the core electrons, in this class at least. And so we took the electron configuration of the central atom, and now we're going to convert that into the orbital box diagram. So we have one box for the 2s, and we have 2 electrons inside of it. Now even though we don't have electrons in the 2p, it's on the same energy level, so we have access to it. They're empty boxes, but we still have access. Now, what we're going to end up doing is adding these together and creating 4 boxes. And so within these 4 boxes, we have an S and 3 P's. And so now what we're going to do is take the 2 electrons that are paired and we're going to split them up. And so that is our configuration for beryllium. Now for chlorine, we're not going to do this whole process with chlorine, but we do have to do the configuration and the box diagrams. So we're going to start with the noble gas neon. And then from there we're going to put 3s2 and 3p5. And so the box diagram for chlorine is going to be 3s with 2 electrons, and then it's going to have 3p and 3 boxes, and then following Hund's rule we're going to add the electrons. And now notice that there's an empty space for an electron to be added. And between beryllium and chlorine, which one's more electronegative? Chlorine is closer to fluorine, so that's going to be the more electronegative element. So that means that, let me change the color. That means that these 2 electrons right here are going to bond within this empty box and then also the other chlorine's empty box. Because we have 2 chlorines, so let's repeat this whole process. And now we have our orbital box diagram. And then finally we add our electrons. And we have another empty space. So notice that we have 2 electrons. Oh, I meant to do red, sorry. We have 2 electrons here. And then we have an empty space for one of them and another empty space for another. So what actually happens in order to form a bond is that this electron forms a bond with this empty space and this electron forms a bond with this empty space. And that's how you get the whole molecule of beryllium chloride. And I didn't draw it correctly, like in a linear fashion. Let me actually edit that just so I don't confuse anyone. Okay. So notice there's no lone pairs on beryllium. There are lone pairs on chlorine, and you just have to check to make sure you're adding the right number of electrons in regards to those elements that aren't the central element. Okay, and right here, this is our central element in the compound beryllium. But what the hypervalency or the hybridization, what it tells us is that there's going to be 2 bonds to 2 chlorines, and there's not going to be any lone pairs. And so the final thing that we have to see is that this is an S p hybridized compound, so sp. If there was an arrow, an electron, in this p, then it would be sp2. But that's not the case, so let me erase that so nobody gets confused. In this case, there's 2 bonds within the sp. So let's do another example just to solidify this. The next example from the workbook is, oh no, let me do it in black, is going to be boron trifluoride, so BF3. And so once again, the first place that you start is with your central atom, so it's going to be boron. And for boron, our configuration is actually close to beryllium. I don't know why I'm doing the orbital box diagram. So we're going to start from 1s2, and then 2s2, and 2p1. And so that's our electron configuration. And we're going to convert that into the orbital box diagram just for the valence electrons. It's going to be 2s2, and then 2p1. And now we're going to add these boxes together, and that's going to form 4 total boxes. 1, 2, 3, 4. So S, P, P, and P. Those are what's available to us. And notice that there's a paired, an electron pair, and so we're going to bump 1 up to the next empty box. That's going to be 1, 2, 3. And now we're going to do the electron configuration for fluorine. It's going to be 1s2, 2s2, 2p5. So we're only dealing with these. We're going to draw the boxes, so 2s, 2 electrons, and then 2p. We have 5 electrons. 1, 2, 3, 4, 5. Okay, fluorine behaves similarly to the previous element that we used, chlorine. And so we're going to see once again that fluorine is going to be more electronegative than our central element. And so we have this empty box right here. And with that empty box, we're going to put this electron inside of it. And then how many fluorines do we have? We have 3. So I don't have to write it all out, just know that there's 3 of these, and so there's going to be 3 electrons going into each of the empty spaces. And that's what creates the bond. So there's going to be 3 bonds, and our hybridization is S, P, and P. So we're going to shorten that to sp2. That is our hybridization. Now we just did 2 easy examples because they didn't include any lone pairs. So let's do an example that does include lone pairs. And the best example that I have right now is going to be ammonia. So we should all know what the structure of ammonia looks like. It's going to be a nitrogen in the middle, hydrogen, and then here's a wedged line just so that we can see that it's coming out towards us, and a dashed line to see that it's going back into the screen. And then we can't forget the lone pair up here. So once we know that structure, hopefully the hybridization will make more sense. So let's do the electron configuration of nitrogen. So let me get my periodic table out. Nitrogen is going to be 1s2, 2s2, and then finally 2p3. So we're only using the valence electrons. We're going to make the orbital box diagram. So 2s, and then here we're going to have 2p. So we fill that in. And then now we're going to add these together, and we're going to make 4 boxes. Now I hope you can see where the issue is going to be. Now notice that in the previous examples, so for example here, we bumped one of these electrons up into an empty box. But what's the problem? We don't have an empty box anymore. All of our boxes have at least something in them. So what we're going to end up having is a pair of electrons and then 3 unpaired electrons. And the hydrogen, the electron configuration is 1s1, correct? So the box is going to be 1s with 1 electron. The more electronegative element is going to be nitrogen, and so in this case nitrogen is going to take the electron from hydrogen. So this is hydrogen's electron, and we have 3 of them. So let me just draw them out like this. This one's a lot faster than the other ones. So we have these 3 electrons from the 3 hydrogens, and they're going to go into these empty spaces. And that's what creates the bonds. Essentially, these lines are the bonds. So we have 3 bonds. Oh, let me put them over here, I'm sorry. So this is our hybridized orbital box diagram. So these are the bonds right here. And then we also have a pair of electrons. So what that should tell us is that there's going to be a lone pair, which is this, and then there's going to be 3 bonds, which are these. And this is S, P, P, and P. So when we shorten that, it's sp3. So that is why ammonia is sp3. Now there's a lot of shortcuts to understanding these, but I think it's really nice to be able to draw everything out. It really helps put all the chemistry together of what we've been doing for this last section. And I just want to give one more example where we touch the d orbitals, just because I think that's important. And once I'm done with that, we can be done with this topic. A good example would be something with iodine. So let's actually try IF5, which is iodine pentafluoride. And so in that example, iodine is a central element. And the electron configuration of iodine, let's start from krypton. It's going to be 5s2 and 5p5. And also notice that even though we don't have electrons in it, we have access to the 5d orbital. There's just going to be 0 electrons in it. And that's because this number right here, it's on the same energy level, so the electrons have access to it, but they're not filling the d orbital yet. That's really important to know for this, because now we're going to draw the orbital box diagram. So this is for S, and then we have P, and then now we have D, which is 5 boxes. 1, 2, 3, 4, 5. So now we're going to fill in the electrons. There's 2 in the S, 5 in the P, and then none in the D. But now we got to add these together and equal our fully hybridized boxes. So now there's going to be 9 boxes. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And now we're going to label each one so we make sure we counted them right. S, P, P, and P, since there's 3 P boxes. And then D, 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 and D, 5 of them. Okay, so now we're going to throw in our electrons. Now notice that there's 5 fluorines. So we need to make 5 bonds. We know that for sure, that there has to be 5 bonds. And we have 1, 2, 3, 4, 5, 6, 7 electrons. So what we're going to notice is that there's going to be 2 that stay together, and then 1, 2, 3, 4, 5 electrons that are going to split up. And that's what allows us to make 5 bonds. 1, 2, 3, 4, 5. If we split these 2 electrons up also, we can make up to 7 bonds. Like, let me show you. If we move that one also, we would make 7 bonds, and that's possible. But in this example, that's not what we're doing. We're only making 5 bonds to fluorine. So that's why we're going to keep a pair together and then separate the rest of them. And so finally, fluorine, we have 5 of them, so let's just remember that. And the configuration is going to be the 2s and then the 2p. 1, 2, 3, 4, 5, 6, 7 electrons, and there's an empty space. So what we see is that this, oh no, I cannot get the red marker. There you go. So this electron is going to add into the empty one. Now because there's 5 fluorines, we're going to have the same situation where there's an empty one here. And so each of these electrons is going to add in to all 5. Just imagine I drew the boxes down there. And so that means we're going to have 5 bonds, and then once again we're going to have 1 lone pair. So from that we can deduce what the structure is going to be. It's going to be iodine. Now just bear with me, I'm not going to draw it absolutely correct in terms of 3D geometry. But here we have the 5 fluorines, and then we have a lone pair. And I draw this just so that we don't lose the lone pair and that we notice that it's electron density. And then remember that none of what we just did tells us about the lone pairs on fluorine. We have to figure that out for ourselves when we draw the structure by looking at the, oh my goodness, I can't remember the term for it, but essentially checking that, the formal charge. So checking that there's 7 electrons around the fluorine when we cut this bond in half, and if there's 7, then that's perfect, we have a formal charge of 0. So I hope that helped checking the structures and also understanding what's going on and why we have lone pairs, why we have these bonds, why things interact with each other, and what the heck electronegativity has to do with anything. Now when it comes to double bonds in hybridization, it's a little more complicated, so we don't have to touch that, but it's just nice to be able to see where the lone pairs come from, how the d orbitals come in even when they don't have electrons in them, and once again the bonding. So I hope that was useful, and let me know if you have any questions.